For us, it's a pleasure today to host this event that starts the first, spreading the word on the activities of the Net Fuels project. And then we gathered, some stakeholders, some people interested in the topics that we are dealing in the Net Fuels projects today here in Terrassa. And we will take advantage of having you here to present to the community what we are doing in the Net Fuels project, and also to take this event as an opportunity for other people working in related topics to present their activities and try, to gather interest from both sides. So the Net Fuels will be later presented by our project coordinator, Andrea Contin, here from the University of Bologna. As you will later see, this is a collaborative project funded by the European Commission under the Horizon 2020 Horizon Europe program. Professor Contin will later explain more details on the project. And this event has been organized by REACH as exploitation partners responsible for the exploitation, and WRG responsible for the dissemination, and us, Leitat, as host of the event. And now it's recording. Okay. So, just with no more delay, going to the agenda, we have prepared an initial introduction to the project so that you can see a general overview of the project, what we are intending to do during these 4 years of project. Then we will go more into more detail at the presentation of the technologies that we are working in the project. And then we will go through different presentations of the invited stakeholders. So we will present different technologies that are being developed within the community that are related to the topics that we are working in the Net Fuels project. Some talks on representing the cluster of bioenergy of Catalonia. So we will have a talk on the biofuels and derivative projects in the oil and gas industry from one partner of the cluster. We will have also a presentation from our colleagues from CETAQUA on another European funded project on biomethane production. We will have then an explanation by ENGIE Spain about the Regenera project, which is a project where we as Leitat are also participating. And then a nice talk by the University of Girona about different uses of the indoor CO2, how we can capture CO2 from the indoor environment and produce products out of it. And finally, Syntec will give a talk on another European funded project on how we can use virtual tools to model and assess different processes. And finally, we will have an open discussion, and finally, we will have some time to share and exchange some ideas that can arise during the day today. And from my side, this is all, and I would give the floor to Andrea. So, Andrea, the floor is yours.
Thank you. So the Net Fuel project started in November last year. So we are now at the first year. The project is a 4 years project. So it will go on up to 2026, when we will have the results. I will go through the objectives of the project, and then I will show you a scheme to understand what we are doing, and then I will talk about part of the technologies or objectives, and then Leitat and Fraunhofer will present specific details on the technologies which are being developed. So what the Net Fuels want to do is to produce carbon negative fuels, which means biofuels or fuels derived from biomass, which has a negative impact in terms of greenhouse gases emissions. And for this, we will make a thermochemical process to produce a hydrogen-rich syngas, a hydrogen separation step to generate a stream which is green hydrogen, oxy-fuel combustion of the tail gas to produce CO2, and then the electrochemical system for production of methane from CO2 and hydrogen. The carbon negativity is granted by the application to the soil of the biochar, so the solid residue from the thermochemical process. Here we see the principles of the project in a very short scheme. So we start from residues, which are either pruning or digestate or manure, which are thermochemical processed through a pyrolysis system with reforming, which will produce a crude oil, so some liquid, which is essentially a biodiesel or something like that, which can be mixed to biodiesel in engines, and biochar, which will be used for carbon negativity application to the soils with a certified carbon sink. The pyrolysis process produces also a syngas, which is rich in hydrogen. So we will separate the hydrogen from the syngas, and the tail gas is sent to an oxy-fuel combustion process. So we burn the gas in an oxygen atmosphere in order to produce a stream of CO2 nearly pure. This CO2 is sent to the bioelectrochemical methanation system. The heat from the oxy-fuel combustion is used to heat the thermochemical process, and the bioelectrochemical methanation will produce methane. We need some electricity to run the system, which will be in principle in the future produced through renewable energies, so no CO2 emissions for that. And crude oil could also be sent to refineries to produce diesel or gasoline fuels. So overall, the system will produce methane, crude oil, hydrogen, which are fuels, with a negative impact on CO2 because of the biochar used in the soil. The project is quite small in the sense that we have a small partnership with 7 partners coming from Spain, Italy for coordination, Austria, Germany, Poland, and England. The partnership is small, but each partner has a specific role in the project. So University of Bologna will do the system analysis of the process. We will make social applications, so to understand how this kind of processes can change the society we live in, and then we'll do also the risk management process. For offer, we put this PCR technology, we implement the hydrogen separation system, and the oxy-fuel combustion for producing the CO2. Leitat will apply this technology of bioelectromethanation, which they developed for some years now, and so the production of methane or synthetic methane through the bioelectromethanation. Leitat University of Technology will make the life cycle assessment of the system, of the process, which means understand the greenhouse gas emissions and the effects of the process on the environment. Moreover, they are experts in combustion, so they will produce a design for the oxy-fuel combustion chamber and for the heat transfer from the oxy-fuel combustion to the pyrolysis in PCR. Ithaca is an institute which is working on applications of biochar in the soil since a long time. So they will take care of application of biochar in field trials and in to the development of a carbon sink certification system, which is expert on business development and exploitation of the project results. So they will produce at the end of the project a business case for the process and potential industrial scale-up of the system. Finally, WRG Europe is taking care of dissemination and formal communication, which is also something they do since a long time. So each of the partners has a specific role and is expert on the field that they will bring into the project. Now, about the pyrolysis system, you will hear about by Fraunhofer visit. They will use an existing system for treating the biomasses, adding the hydrogen separation step, the oxy-fuel combustion to produce the CO2. And then Leitat will take care of the transformation of CO2 into methane by using this bioelectromethanation system, which will be described later. Is essentially the hydrogen is produced via electrolysis of the water, and then the hydrogen is used to transform the CO2 into methane. The main point in next fuels is to produce this carbon negative fuels. So here you see a massive energy balance of the system. The unit is 1 kilogram of CO2 sequestered through the biochar, and summing up all the numbers which are here, we will gain about 80 grams of CO2 per megajoule of fuel produced using this the present carbon intensity of electricity. We need this kind of energy for heat and power. The present carbon intensity of electricity means that now part of the electricity is produced by burning fossil fuels, part from renewable energies. In 2030, when the share of renewable energies will be higher, we will increase the gain from 80 to 105, and then as the renewable energies increase in the share of electricity, we will gain more. Another important parameter, which was part of the proposal, is the efficiency to transform the biomass into fuels. And this efficiency is just the fraction of the input energy which goes into fuel energy. The input energy is the energy contained in the biomass, plus the energy that external energy is used for running the system. And then the fuel energy is the energy content of the different fuels we produce through the system. So the ratio is now about, considered about from 55 to 63%, which means that the system gains a lot of energy. So the energy output is very positive and represents about 60% of the energy put into the system. We studied the impacts of the project in our proposal. This is quite a complicated graph, but it is used to put into relation the key functions of the project. So hydrogen, power to gas, system analysis, value chain stations, and so on, to the outcomes, which is increased bioenergy efficiency, sustainability, generate negative emissions from biofuel production, and increase the sustainable biomass resource utilization. And all these functions and outcomes, they project into impacts which are linked to the destinations which the European Commission considers important, which are fostering the European global leadership in secure, affordable, and sustainable renewable energy technologies, development of energy system grids and storage, and carbon capture, utilization, and storage. So these are the three main objectives of the European Commission, and we will contribute to each of them to new technologies, reduce cost, improve efficiency, better integration of renewable energy into fuel-based solutions, reinforcing European scientific basis, more effective market uptake, based in renewable energy, and enhancing the sustainability value chains. For the first, for the second, improve energy storage technologies, and increase the flexibility of the energy systems. And then, for the third, improve the feasibility of integrating CO2 capture into the system. What we expect from a widespread introduction of our technology is at the end to contribute with about 7% of the total transport fuel consumption in 2030. Because what we do is we take available biomass, which we consider between 200 and 350 megatons per year, ensure CO2 sequestration at the level of 150 megatons per year, ensure 110 megatons per year of net negative emissions, and use 110 megatons of oil equivalent as fuels in 2030. And this will allow us to cover a share of 7% of total transport fuel consumption. One of the main objectives of the project are also to test the sustainability of the project in terms of greenhouse gases emissions. And for this, we will implement a dynamic model, which is something new with respect to standard life cycle assessment, because life cycle assessment is a picture of the state at a certain point in time and space. What we want to do is to extend this analysis to different times, in the sense that the society progresses during time and conditions change. So in order to validate negative emissions over time, we need to make a dynamic system which evolves with time. The very introduction of our system will change the overall picture. So you need to follow the change in society before to prove the negativity. We want to develop a certification guideline, because one of the main points for carbon negative fuels is to certify the carbon negativity and eventually to produce carbon credits for financing the projects. And then validation of the specific biochar we will introduce in the project as soil amendment. From the social policy and acceptability, which is another specific point of the project, we will connect our system to the general social system with the aggregation of data at the regional level. So in order to understand which are the barriers and which are the limits to the application of the net fuels technology in society. And also we will, as I said before, develop a scheme for industrial application of the system, and we will assess the business potential of net fuel solutions. And then acceptability from the society is a very big point, because we have the barriers to the introduction of biofuels or fuels derived from biomasses, which may go against food production. So there is let's say, we need to have a clear explanation of our use of, let's say, residues only for producing our fuels. And so there is no interference with other uses of biomasses. All this is done through 6 work packages. We have management, coordination, and dissemination exploitation, which are transversal. Then we have 2 main technical work packages, one for the thermochemical conversion and the other for environmental chemical processes. These 2 technical packages are connected to a business development package, and all this is analyzed from the sustainability point of view. And each work package is led by one of the main partners of the projects. So thank you for your attention. I'm ready for questions. Essentially, I'll offer later to present the technologies, and then we can have a discussion.
Thank you very much, Daniele. Thank you, first of all, our colleagues from Leach and Leitat for organizing the event. I will present you first in a very short and give you some information about Fraunhofer, Umsicht, and then present, well, some slides about the big picture regarding negative emission technologies. I don't know what background all the others have. It might be helpful to have this this picture too, and then explain a little bit about, on the one hand, TCR technology, which is one key of the project itself, plus what we plan for oxy-fuel combustion. So, some words about Fraunhofer Umsicht. Our vision is to be a pioneer for a sustainable world. We want to contribute to solve major challenges like climate change, energy supply, and raw material security. Fraunhofer itself is a non-profit organization to do applied research, so to close the gap between fundamental research and the application. We do not produce products, but we try to help industry to create new products and services. And there are over 60 different institutes, and the institute I'm allowed to work for is Fraunhofer Umsicht. That's for environmental safety and energy technology. And it's the 7th largest Fraunhofer Institute, with over 600 people working there, and over close to 80 million, a budget of close to 80 million euros, with 2 locations, one in Oberhausen, North Rhine-Westphalia, and one smaller one in Sulzbach-Rosenberg, Bavaria. That's where I'm coming from. Yes, the topics of Fraunhofer Umsicht itself, the main focus of our activities is in 4 areas. One is carbon management, where net fuels is also connected to. Generally, the circular economy, and creating local energy systems. Net fuels is also contributing to this part, and it's also connected to green hydrogen, the 4th of our main research activities for the overall institute. Maybe a closer look to what we do in Sulzbach-Rosenberg, the smaller site with about 100 people working there, and 3 departments. One that's called Advanced Carbon Conversion Technologies. They are doing all the research going on with pyrolysis itself, from biomass, plastics, and so on. Another department with focus on secondary resources and assessment. They are doing waste and research strategies mainly. And department I'm managing is the clean combustion processes. So we are working on all kinds of combustion processes, always with the goal to reduce emissions of pollutants, reduce emissions of CO2, and to implement these technologies in applications with the focus of the use of especially biomass. And we see the biomass especially in two areas, which is on the one hand for process heat applications, and in combination with carbon negative process chains like we have here in Netfuels. As I told you, just a few words about carbon dioxide removal in general, with some slides from front of the colleagues, just to give you the big picture from the IPCC report, and to give you an idea about why it's so important to make research in the field of negative emission technologies. If you look at all the different scenarios the IPCC calculates, basically all scenarios that limit the warming to 2 degrees Celsius in 2100 include negative emissions and the corresponding technologies. This is mainly because on the one hand there will be some emissions that cannot be avoided. They will still be there even if we are producing all our electricity with renewable energies and all processes are sustainable. There will be still some emissions, and on the other hand, we are filling up the atmosphere right now with CO2, and we have to find some measures to reduce it again. So basically, this shows the different evaluations or different aspects about the amount of negative emissions that might be needed to keep the temperature to the 2 degrees, 1.5 degrees. And you see that the amount, of course, depends on the different simulations, the different scenarios, and their boundary conditions. But just looking at the size with 260, in this case, 260 gigatons of CO2 that have to be removed, that's really a large amount. And this shows that the task is quite huge, and different technologies and different pathways will be needed to achieve this. Also, maybe just a short overview as well about the different possibilities to achieve negative emission or different negative emission technology pathways. First, for us, the most important tool from our side, from the Netfuels perspective, on the one hand, the biochar carbon dioxide removal, producing biochar with pyrolysis or other products, and sequestrate the biochar in different applications. Here it looks like the soil, but biochar is a quite versatile product that can be part of many different applications. The other part is bioenergy, carbon capture and storage, which is a huge area. If you consider how versatile also bioenergy applications is, the many different technologies, conversion technologies, the many different, all these can be combined with CO2 capture and storage and utilization pathways. So a quite large area. What we do in Netfuels is connected to this. We will go with oxyfuel to make an efficient carbon capture. And yeah, the other options, probably you're familiar with them as well: direct air capture, enhanced weathering, afforestation. So using areas to create forests, to use the storage capacities of forests, soil carbon sequestration, and the ocean alkalinity enhancement. For us, as I mentioned, those two are the most important from the net fuels perspective, as we are more or less combining these two parts. Yeah, that's in general our vision to create an efficient combination of BECCS and PUCs in this case via oxy-fuel combustion. The idea is to, on the one hand, we have the pyrolysis unit producing also an gas. Could be also biogas or other gaseous biogas components. If we from the site or the situation, the infrastructure, it's possible to link this to electrolysis. In the most important cases, in the most cases, it's the most important part is producing for sure hydrogen. But if you produce hydrogen, there will also be a lot of oxygen available, and we think this is a huge opportunity to use this oxygen to go for oxy-fuel combustion. The idea of oxy-fuel combustion is mainly that you are not using air, but just 100% of oxygen, make the combustion, which results in an flue gas that consists, in an ideal world, out of CO2 and water. And water can be easily condensated, and then you have a very pure, quite pure CO2 stream, much easier produced and much easier provided than with other technologies for carbon capture. Yeah, and mainly that's the idea of connecting these two parts. And now I will go a little bit more into the technologies. One important part is the TCR, the thermocatalytic reforming technology. This was developed at Fraunhofer Umsicht in the past 10-15 years. Yeah, I'll try to show you a little bit about the process itself to have a better understanding about it. It's as Professor Constantine already mentioned, it's a pyrolysis process with a two-stage system. On the one hand, the feedstock goes into the pyrolysis unit. It's a screw reactor, auger reactor with an intermediate pyrolysis. It's heated from the outside to temperatures around 500 degrees. And here the pyrolysis takes place. Then the jar is going to the reforming step, to the catalytic reforming. And here we have a second stage, the post-reformer system, with higher temperatures of 700, 800 degrees, depending on the situation. And this second stage helps to improve the quality of the gas, the oil, the jar. And then we are producing three main products. The one is the biochar, the carbonisate, then the oil, and the gas. And for TUSIN fuel, for net fuels, sorry, all these products are very important. Yeah, maybe the one advantage is that there's the possibility to utilize different biogenic residues, and decentralized application is possible. The product of the syngas itself, regarding the hydrogen contents, of course, depends on what kind of material you use. The oil, the main advantage is that is thermally stable compared to maybe other pyrolysis processes like flash pyrolysis, or the oil quality is very good with high quality. Thermally stable means that it can be mixed with biodiesel. It can be used in refineries directly. This is the main advantage of the project of the process, and the char can be used for sure depending on what kind of fuel, what kind of feedstock you use. For example, for on the one hand, sure, for energetic use, but what we like to achieve is more applications that allow carbon storage, applications in the soil and in products that make sure that the carbon is sequestrated. Yeah, as I already mentioned, one of the big advantages is that there's a huge variety of feedstocks that can be used. Maybe some restrictions that are given. It's not that we can take everything. The material has to have a content of dry matter of more than 70%. For many feedstocks, drying is required, and it cannot be in the form of a dust particle, because otherwise we will have a blocking of the system, pressure drop will increase and things like this. So there are for sure limitations. But yeah, we have tested in our different equipments until now more than 90 different biogenic waste materials from many different industries and applications to find to gain information, to create a database, and to find solutions for our customers to find different options for the utilization of these residues. Another important point is as I already mentioned, the thermal stability of the TCR oil. In one project we already had with two-syn fuel. I will refer to that later. We showed that it's possible to grade up our TCR oil to diesel or other fuel fractions, and we could show that the diesel we produce meets all requirements that are also given to fossil diesel. So the quality is really very high, can be used in mobility, automotive applications. And what we showed there is that we can go the path via hydrogenation. We use hydrogen plus a catalyst to make a hydrotreatment of the TCR oil, and then with distillation, creating different products like diesel or gasoline. Yeah, maybe to show you with what kind of equipment we operate. We have one lab, one pilot scale unit. The lab scale unit is operating with 2 kilograms per hour. Easy to make test runs to gain information about the feedstocks and about to make variations of process parameters and to make first tests. The pilot scale unit with 30 kilograms per hour. Yeah, okay, maybe the process can be seen very good. The feedstock comes here. Here's the main pyrolysis part, the post reformer itself, and then the container for the biochar. In this area, this is also the size where we operate then the net fuels technology. So this size will be used to combine it with the pressure swing absorption to get the hydrogen on the one hand, and the tail gas will be used to burn it with oxy-fuel combustion. But this in the next step. The next step of the development is the TCR 500. So we demonstrated in the already mentioned project 2-syn fuel. We demonstrated this technology in a scale of 500 kilograms per hour. So and at our site in Hohenburg. What I showed you in this small application is now in a quite larger situation. The project was focused on the utilization of sewage sludge. This green part over there is the pyrolyzer itself, so the main screw reactor. Over there is the product gas treatment with cyclone filter, electrostatic precipitator. Then there's the PSA for the hydrogen separation, and over there the HDO unit to make the hydrogenation process. There's also a CHP unit. So that's the travel we made from 2 kilograms over 30 kilograms to 500 kilograms, and that's where we are right now. We try to bring this technology to the market, but that's where the activity for Fraunhofer also stops. As I told you, we are not producing products. We need and we are looking for companies to go this path with us to move forward and to move this technology into commercialization. Yeah, to sum TCR technology up, it's a pyrolysis unit with the possibility to utilize biogenic residues to produce sustainable fuels. It's possible to go for decentralized applications. Regarding the input material, it's quite flexible. It's possible to go for CO2 neutral or ideally CO2 negative products, energy carriers. The syngas we produce is rich in hydrogen, and the carbonate, for sure, depending on what kind of feedstock you use, can be used for soil applications and sequestration. If you want to know more about TCR technology, there are some links, or for sure I'm also looking forward to your questions or discussion afterwards. Yeah, maybe some words about the oxy combustion. Here we are at the start. As I mentioned, the basic idea is to use oxygen that is available from electrolysis, burn biogenic gases with pure oxygen, and yeah, that's where we are. We want to build up, or we are about to build up an unit and test rig with about 50 to 100 kilowatts, where we can use, on the one hand, TCR gas, natural gas, or other gaseous components. And that's basically the simplified overall structure of what we are building up. We have the burner system that can use biogenic gases or natural gas from the grid. I told you that we are using pure oxygen. For sure, if you use 100% oxygen, combustion temperature would be very high, which would cause massive problems for material stability. So we are diluting the oxygen with CO2, which is possible over the recirculation fan, which we can use in 2 ways, either right after the heat exchanger or after the condenser. So if you're the burner and combustion chamber, the heat exchanger cooling the gases down to a temperature of about 120 degrees, and then a condensing unit where we are condensating the water, or as much as possible of the water, so that we have here a carbon dioxide stream or source. Well, that depending on the quality of the oxygen, depending on the quality of the fuel, we might achieve qualities around 95% of carbon dioxide. plus minus some percent. That's the range. Yeah, maybe some additional information for the startup for our tests. For sure, we operate with gas bottles. Also for the startup, we have some additional carbon dioxide available to come quicker to certain situations, and we can start up our system with ambient air. So we are flexible regarding the mixtures. The process itself is right now under construction. First equipment is available. Some is still in purchase. Yeah, but we hope that we will start stepwise. First, operating it with natural gas. This will be at the beginning of the next year. Then we will start to attach it to the TCR unit, and yeah, moving forward in this way. Maybe as an overview for the oxy-combustion. If oxygen is available, that's the precondition. It's I would assume the cheapest and easiest way to make carbon capture in gaseous form. We can use various biogenic gases as a fuel. For sure, for us, important pyrolysis gas, but also biogas could be possible, and gas from gasification, as long the gasification agent is not air. If it's air, then you have high nitrogen contents for sure, also in the syngas, and then it doesn't make sense or doesn't make much sense. Yeah. We are still in the design of the testing environment, combustion with around 50 kilowatts. We assume a purity of, from the start, of 95%, which can be increased with better drying and further steps to optimize it. And we go for flameless combustion, as it gives much flexibility in the operation and use of lower calorific gases fuels. Yeah, that's the overview for now. Thank you very much for your attention, and yeah, if you have questions.
Okay, good. So, yeah, I will go on with a presentation of the bioelectrochemical methanation unit you already got. To know that this is the last step for the conversion of the CO2 content of the tail gas of the overall process, and it is the technology that we develop here in Leitat. This, you already saw this diagram before in the presentation of the net fuel concept, and it represents the general architecture of a bioelectrochemical system with two chambers, two electrodes, an anode and a cathode, externally connected by an electrical circuit, where we put a power source. And in these two chambers, we perform with two semi-reactions of oxidation and reduction. The one of our interest of CO2 conversion to methane happens on the cathode, bio-cathode, so it is biologically catalyzed by microorganisms that are able to collect the electrons passing from the electrical circuit and use them to reduce the CO2 directly or indirectly through hydrogen production. And on the opposite chamber, we have the counter reaction that we need as an electron donor of the overall process. And in this case, we will perform water splitting. Why? Because we need the oxygen for the oxy-fuel process developed by Fraunhofer. As you see, each reaction that takes place at a certain reduction potential, And due to that, the thing that on the anode side we have a higher reduction potential than on the cathode side, both direct or indirect methanogenesis, we need an additional electricity supply to the system. That in theory is 1.23 volts, but then due to the energy losses of the system, at minimum, we will have to add 1.5 or 2 volts to the bioelectrochemical system to run out these reactions that we want. As I said, the cathode is a biocathode, is catalyzed by electroactive microorganisms. In general, in bioelectrochemical systems, there are these model electroactive microorganisms, Zeobacter, fructoreducens, Salmonella, ometensis. In general, this kind of microorganisms can be found in natural inocula sources like activated sludge or sediments from riverbeds, anaerobic sludge from anaerobic digesters. And what we want is that these microbes colonize the electrode and or electrodes or of the system, in this case the cathode, to act as catalyst of the reaction happening there. Again, methanogenesis, electromethanogenesis. This is what is happening on the cathode, and is the last reaction step of the process that is anaerobic digester. But in this case, in order to reduce the CO2, the reductive power is given by the biocathode, by the cathode, and there are different mechanisms for electron transfer from the cathode to the CO2 by direct contact of the microbe on the electrode, or through mediator substances, as for example the hydrogen that can be produced there abiotically. And yeah, and here the idea is to use this technology as an alternative to chemical or biological methanation as other power to gas technologies that are already at a higher TRL. And why we study the bioelectrochemical methanation option, because it has different potential advantages compared to the other technologies in terms of conversion efficiency, especially the mild operation conditions that are needed in terms of operation temperature. We plan to operate the net fuels system at 35 degrees, and it allows, well, operating pressure again of atmosphere or a few bars. It allows to reach high methane purities of the output gas, and it has been shown to be resilient to on and off periods in case of being run by renewable energy surpluses, and therefore subject to periods where we can not have this renewable electricity available. Well, bioelectrochemical methanation has already been studied since several years. Here in NetFuels we have some KPIs, but I don't think that I have listed here. But anyway, of productivity, of efficiency, and we are targeting different points for the optimization of the technology. First of all, for the solubilization of the CO2 coming out from the PCR and oxy-fuel process to the liquid electrolyte that we need to run the bioelectrochemical system, and we plan to do it by hollow fiber membrane contactors. That there is a group here in Leitat very good on this technology. And from the bioelectrochemical cell, we will be studying different cathode materials in order to increase the performances of the system. We selected and enriched a biofilm with rich in hydrogenotrophic methanogens that we need for the reactions to happen. And we will optimize the systems in terms of applied voltage. We try to optimize the ratio between the electrode surface and the volume of the reactor. And we will have to fine-tune the process in order to reach a high quality fuel gas at the end, and minimizing the presence of excess CO2. Here in this slide, I report the principle of the CO2 absorption through hollow fiber membrane. Is a process where we have these membranes. On one side, we have the gas reaching CO2. On the other side, we have the electrolyte that we will need in the bioelectrochemical setup. And due to the gradient of concentrations of CO2 between the two medium, we can achieve a cross flow. And the important thing is that this crossover is, due to the material of the membrane, will be selective for CO2 and will keep out other possible impurities that are present in the tail gas. Regarding the characteristics of the electrodes that we are looking for the cathode of the bioelectrochemical system, in previous studies, a lot of different carbon materials have been used that have a lot of qualities that microbes like electroactive microbes like electrical conductivity. They are electrochemically stable, so resistant to corrosion. They biocompatible with a high specific surface, mechanically strong, hydrophilic. A lot of these materials are carbon-based, but we plan for net fuels also to look into metal based electrodes like stainless steel wool. Okay. Regarding the reactor architecture itself, we saw it before from the diagram. That is two-chamber cells. There are different setups that have been studied in the literature, starting from H-type cell, that is the most common setup for laboratory proof of concept experiments, but it is not scalable. And for this, in Leitat, we move it to flat plate reactors like this, where we can reduce the distance between the two electrodes. We can achieve higher surface to volume ratio, and therefore reducing of your potentials and the energy losses of the system, increasing the energy efficiency of the process. Part of these other reactors being studied in the literature, like column based with moving bed cathode. each one have its own advantage or disadvantage, but for net fuels, we will go for flat plate ones. And here in this diagram is represented the process flow diagram of this last technology of the overall net fuel process. So we have, well, again, also as Frankfurter also here, we will start from CO2, but then the aim is to test the real gas coming out of TCR and oxy fuel that initially Frankfurter will send to us by the bottles, and this will pass from the hollow fiber conductors to solubilize the CO2 into the liquid electrolyte stream that enters in the cathode chamber of the bioelectrochemical cell, and where is will be converted to methane. Ideally, in one passage, we should achieve almost all the consumption of all this CO2 conversion to methane that will be extracted in a separation unit, and then the electrolyte will flow again to get recharged of CO2. And on the other side, we will have this counter reaction of water splitting with oxygen production, that also will be measured and ideally will serve for the oxy fuel process. The idea is to, if you remember the presentation at the beginning, is to build a prototype able to treat 50 liters per day of CO2. We will test it first here, and then it will be sent to Fraunhofer in order to be coupled with the other processes that are being developed there and have the overall prototype of the net fuels technology. Thank you for your attention.
So I did not have a chance to introduce myself before, so I'm Fatima Darwin from Reach for organizing this event. And now we still have some minutes before we go for the break. So I would like very much to take this opportunity to invite one person from each of the partners to come over here. And we're trying to get some conversation with our guests today. So please, Andrea, could you come? I don't know, Eduardo, Daniele from Leitat, and Martin, and Niklas and Andre Niklas from Dhaka did not present, and Andre from Sut. Can you please come? So the idea is that we encourage you to take this opportunity and bring some questions from your side and ask them some questions from their presentations or from our project altogether. And well, okay, let's start here. I will pass the microphone to you. Could you please also introduce yourself?
Yes, hello, thank you for the presentation. I'm Claudio Desi from the University of Reggio. I have a general question about the project itself. Have you considered as an alternative to produce directly the fuels from the syngas, for example, produce methane from syngas or even some more valuable fuel? How does it compare in terms of economics and scalability with your approach?
Yeah. Well, directly from syngas. On the one hand, we have the syngas, and for sure it's possible to directly use the syngas. The separation of hydrogen is just one opportunity that we show that is possible. For sure, it's also an idea not to make this separation. This will in the end depend on economics, on the situation, what a product creates the higher value in a later application. This is mainly to show it's possible to produce this, on the one hand, this variety of fuel products. On the other hand, to show that the quality and the variety of these products is possible. And for sure, all these products, there are different possibilities for applications. We chose this combination, this set of products to go for. And for sure, in the process before, we discussed about different options and what to do. But in the end, it was the decision to go for this set of parameters and variations.
Okay, thank you very much.
We may add, you certainly can produce methanol from syngas, for example. Or you can just burn the syngas and produce energy. But in a way, this is a more complete use of all the products from pyrolysis. And also,
yeah, I just want to add to this. This gives also more flexibility with regard to the feedstock, because this process will work with any feedstock, and this is the clear goal, as Martin showed, that it works with a broad range of residual materials. And the more you closely would try to expect stuff from the syngas directly, the more dependent you would be on a certain feedstock quality. So this process will be also more robust with regard to the fuel flexibility.
Any further questions? I would like to more or less encourage you to think about how is your expectations about the results of our project in the work you do, what kind of applications you could envisage, if you have some as early adopters of our technology, what kind of results you would be willing to be following it up. So any questions in these directions for us? Go ahead.
Thank you. Thank you very much. My name is Antonio Jimenez from the Spanish water utility Aquaria. And because of this, I'm particularly interested about the application of your solution that you are proposing here in sewage sludge and digestate. I have a specific question to Martin about the TCR technology. As a private company, even if we are in an innovation department, we don't have to forget some key parameters, and we are specifically very interested in the indicators about the solution. You said you already test the solution. You already upscaled this solution to a reasonable size, about 500 kilograms per hour. It's big enough. My question is, did you already make some estimation about, at this scale, about the performance in terms of, for example, energy consumption or OpEx, or the expenses in the operation? The cost, all these kind of things that may sound interesting to a private company.
Yeah. Well, that was mainly the goal of this project I mentioned, Tusing fuel. We had this plant in operation in continuous operation for several months. And the goal was to get a better understanding about operational costs and so on. So yes, there are information in this direction, also business case applications or considerations for the technology. And if you're interested, I can link you to our colleagues who could provide you with detailed data on this. For sure, it's still in a pre-commercial phase. Main goal is to reach the goals of the research and development projects in this case, but it's as you mentioned, it's a size where it gets close to commercial application and important information to be gained.
Thank you, Martin. Any further questions? Okay, very good.
Hello, thanks you for the presentation. My name is Federico Ferrari from Leonardo. I represent for Marielle. I've seen a nice slide about comparison of technologies of biomethylation. And I was wondering if you took into account the electrolysis, the electrolysis step for the other technologies that are not electromethylation. Because you don't need anyway hydrogen in the steps in other technologies, while for the electromethylation you don't need it.
Well, indeed, yeah, as you say, for both chemical methanation or biological, you need an electrolyzer producing hydrogen in and in the biochemical methanation one, the advantage is that it produces directly inside the reactor, and you can tune the production to the rate that you want to convert this CO2 and not having hydrogen surplus in the effluent gas. And yeah, it's one of the possible advantages of these technologies compared to the other two.
In the numbers, there's already calculated
The numbers in the numbers of energy consumption, energy. I should check again the table, but I think that it's included. It's a comparison between the three. Actually, I did it some time ago, but I think it's included.
Any other? Thanks a lot. Any other question for the moment? I think this is a very good moment that we leave the questions, the complementation of the answers for our coffee break. We are very much on time, so I thank everybody for Deafuse partners for having done this excellent presentation to our stakeholders community here in Spain. And I thank you also for coming, and let's have a break now, and then we continue with the guests' presentations. Thanks very much. Thank you. Now we will have the stakeholders' presentations. And as I was saying before, I take this opportunity to thank every of the invited guests here that they took their availability to come and to present about their work to us. And the recording on Teams will be available then for you after editing. Our next presentation now is about biofuels and the derivatives projects in the current oil and gas industry. And we invite then Antonio Sanchez from Cluster Bioenergia Catalunya to come here and present it to us. Thanks very much.
Good morning. My name is Antonio Sanchez, and I'm one of the project managers in the Industrial Plants Division of the CETI Engineering Group. We are members of the Bioenergy Cluster Catalunya. How many of you have even heard spoken about the cluster? Well, let me begin introducing ourselves. The Bioenergy Cluster of Catalonia integrates over 100 companies and entities from the private sector and the public sector interested in promoting efficient and sustainable use of bioenergy. We are looking forward a competitive and circular economic model. Nowadays, we are the main bioenergy cluster in south of Europe. This is our values. And the mission of the cluster, the cluster aims to promote the sustainable and efficient use of bioenergy. We integrate 2 working groups. Oh, excuse me. Yeah. Second. Here. Yeah, we integrate two working groups, one for biomass and another one for biogas. The cluster services aims to promote the sustainable and efficient use of bioenergy. Yeah, and this is our service. Business development, visibility, promotion, representation, that kind of things. But who are we? We group different sectors and stakeholders about production, distribution of biomass and biogas, machinery and equipment, and for both of them, research and innovation, and engineering and energy service. This is we. We are coming from the city engineering group. This brings us to engineering service. Yeah. And we are dedicated. Our business is innovation, consulting, engineering, and outsourcing. Our mission is to provide innovative and technological solutions to make our customers more effective and competitive. And our vision is to be the company where engineers love to work. We are dedicated to providing engineering support, mainly to Repsol and Cepsa refineries and other industrial plants throughout Spain. A quick heads up, we are engineers that love engineering challenges. So our success is based in four Ks: team experience, deliverables quality, proximity, and customer service. So if we speak about current projects in Spain, we can speak about e-fuels, okay, petrol and diesel replacement fuels produced using renewable electricity, water and CO2 from the air. These kind of fuels are climate neutral and can be used to power vehicles, cars, trucks, even for airplanes or ships. These kind of fuels are similar to actual petrol or diesel, so there is not a big difference for the final user. This is the difference with the electric vehicles. So in Spain, the first synthetic fuels plant is being promoted in Petronor in Bilbao. It's powered by renewable electricity, yeah, and they use an electrolysis and separates oxygen and hydrogen and captures CO2 from the emissions from refinery. This kind of use, we can obtain zero net emissions. We can obtain it, and we can use in current automotive industry with zero emission. Some numbers of this project: we have 10 megas electrolyzer and 2,100 annual tons. It's more or less 8,000 barrels equivalent. It must be operative in the second half of 2025. So biofuels are a promising source of renewable energy, but this use of biomass is not new. At the most basic level, humans have been using biomass for energy since prehistoric times. Technically, a biofuel is any biomass that has been converted into fuel. This can include bioethanol and mineral biodiesel, but it can include firewood and animal dung. So the first generation are derived from food crops like corn and sugarcane. This is from the Second World War. World War, the vegetable oil was used to replace petroleum. Then we have the problems with the 60s, motivated greater investment in biofuels. This first gen is they compete with food crops for land and resources. But 2021, 40% of corn went to bioethanol production, although only 5% of the nation's energy needs. As second generation, scaled now, biofuels are associated with in vegetation, usually cellulosic crops or residues from agriculture and forestry. These fuels are supposed to reduce competition between energy and food needs. The real impact may be more complex. Some second generation biomass provide food for livestock, while others require a significant amount of water. And then a third generation biofuels are associated with algal biomass. Algae are promising biomass alternative as they multiply rapidly and remove large amounts of CO2 from the atmosphere. And then we have waste-based biomass fuels, with other processes generating materials that also provide the source of fuel. For example, decomposition in landfills produce methane-rich gas that can be combusted for energy. So one of our clients is Vertex. Vertex Bioenergy is the leading bioethanol producer in Spain and France. They have 4 operation plants in Cartagena, Coruña, Salamanca, and Arans in France. This renewable and local fuel significantly reduce the CO2 emissions. Yeah. Compared to gasoline, this contributing to environmental improvement and energy independence. In addition, this process produces animal feed materials, corn oil, electricity, and captured CO2. We in City Engineering have developed a capture CO2 plant in Vertex facilities in Cartagena for Nippon gases. They use the destination for this CO2 capture, it's for alimentary industry. But we can obtain biomethane and natural gas. And definitively, biomethane and natural gas are the same molecule. The difference is how it's obtained. In this diagram, we can see that from waste, agriculture, organic, domestic or industrial, we can obtain the digestion process and obtain biogas. We can use to obtain electricity and in our cogeneration work done. We obtain fertilizer too, and we can make a second process of draining to obtain natural gas. And nowadays, oil and gas company, Repsol, Cepsa, Enagas, Reexis, Naturgy, even investment groups like Goldman Sachs, everybody is planning to build biomethane plants in Spain. We can read every day about this. The reason behind this race is the guarantees of origin market. Guarantees of origin is a certificate that detail the origin of our renewable electricity or fuel. In principle, they allow for the transparent and confident trade of renewables. There are economic benefits for using gas with guarantees of origin in several EU countries. So these countries are interested in this market. According to 2023 SEDIGAS study about biomethane capacities in Spain, we can have more than 2,000 plants of this kind. But nowadays, there is another process to obtain biofuel. For example, Certego is a company from Urbaser Group, who offers environmental solutions for the industrial sector. They obtain recycled fuel from Marpol. We are working with Certego in several plants for maintenance engineering. And another project about Repsol, who is working in different projects to obtain biofuel in Tarragona, Coruña, Petronor, Puerto Llano, and Cartagena. We have been working for Repsol on C43 project in Cartagena. This is the first refinery project with biocombustibles. And we developed the electrical units and several piping lines. They are working in different projects to obtain biofuel, even for planes or ships, not only for automotive engineering. In Petronor, is being developed too, for example, a pyrolysis plant projected in waste and to capture CO2. This is mainly used for hydrogen valleys like BP or Sirius in Cartagena. And we are collaborating with Cepsa, who is developing 2 gigas in Cádiz and Huelva. They want to produce 300,000 of tons. In conclusion, there are many projects and investment on the table that translate into opportunities. That's all. Thank you very much.
To go further on the presentations and we leave the discussions to the end. The next presentation will be this Sempre Bio project, new cost-effective solutions to produce biomethane, and Alejandra Cordova, did I speak it right? From Setaqua will present it to us. So please, Alessandra. So I will give you a code. If I stand up, that means it's time to conclude, okay? Thanks very much.
Oh, thank you. So good morning to everybody. My name is Alejandra Cordova, and I'm from a project manager at Setaqua and the coordinator of the Sempre Bio project. Thank you for the opportunity to be here today and to share our project with all of you. Let's first a brief introduction of where I work in. I'm from Setaqua, the Water Technology Center, and we are a public-private partnership model that focuses on research and development in knowledge-based services and digital services. So let's begin with the Sempre Bio project. The Sempre Bio project, the acronym is Securing Domestic Production of Cost-Effective Biomethane. The objective of the Sempre Bio project is to demonstrate novel and cost-effective ways to produce biomethane with different solutions and pathways, essential for achieving the European Green Deal and climate energy objectives for the 2030 and the 2050, and also as well as to increase the market acceptance of the biomethane production in the world. The Sempre Bio is a 9.9 million euros project funded by the European Union and is under the Horizon Europe program. It's a project of 42 months during that we start in November of the last year and we end in the April of the 2026. We are made of 6 countries, 6 different countries: Spain, France, Belgium, Germany, Denmark, and Norway. And we are integrated by 16 different partners with different expertise, beginning from research centers, universities, end users, the industry, a farm, and also a consulting agency, of which Setaqua is the project manager of this project. At the Sempre Bio project, we established 3 different European biomethane innovation ecosystems. That these are the representative different ways that we produce biomethane across Europe. The EBIS, as we call it, we have 3 different case of studies. One is in Baix Llobregat in Spain, the other one is in Bourges in France, and the other one is in Albuquerque in Belgium, where 5 different technologies will be implemented and tested. This EBIS will facilitate a long-term replication, creating an active flow of information, and this information will create future investment opportunities. So I'm going to show these different case of studies and which kind of technologies we are using. In the case study number 1, that is in Spain in the Baix Llobregat at the wastewater treatment plant of the Aigües de Barcelona, we'll demonstrate a biomethane production technology that will allow to valorize the current biogas stream produced to generate this biomethane. Here we are going to build and operate a plant to convert the biogas to biomethane using an innovative combination of technologies, is the electrolysis and the CO2 biomethanation, where the regenerated water from the tertiary system of the wastewater treatment plant will be pumped through a reverse osmosis system to generate the mineralized water from the electrolyzer. The hydrogen produced in this electrolyzer will be react in a biomethanation reactor with the CO2 to obtain a 95% of purity of biomethane, purified from volatile acids and also from siloxanes. The produced biomethane will be compressed and for storage, and there will be used in the system public of transport of Barcelona. The produced biomethane will be sufficient to fuel 2 buses to daily route for 150 kilometers. In the case study number 2, that is in Bourges in France, is that at the Ecopole Marmagne site, will produce biomethane from non-digestible urban green waste. Here is a pilot of biomethane production plant that will be built and operate from wood biomass and organic biomass from the city of Bourges. The innovative transformation of this wood biomass to biogas will be with a combination of these 2 technologies, the pyrolysis and the CO2 methanation, where the wood waste undergoes to a pyrolysis process that we see in the other projects. And here we are going to have a syngas that then we are going to pass through the biomethanation reactor to obtain a biogas. This biogas will be aggregated to biomethane, and this biomethane will be injected into the already network using in the existing facilities. In our third case of a study, that is in Adinkerke in Belgium, this case of the study is a farm that without having a natural gas connection and low gas biogas production. So these 2 characteristics make impossible for a small biogas producer to have a sustainable plant. So that is why these novel solutions and these will demonstrate that bring the profitability to small scale plants through biogas purification and liquid biomethane production. The liquid biomethane production will be stored locally, and while different ways to valorize the CO2, such as in polymers or proteins, will be studied. The aim of the operator here for the farm is to feed almost exclusively the co-fermentation with manure and only a partial portion with some organic waste just to optimize the process. So with this fermentation, distillation farm will be being energy neutral. The goal is to demonstrate that the potential of low scales to produce liquid biomethane and liquid CO2 from biogas with an integrated cleaning process. And the selected technology to go through this process will be by the cryoseparation process. In our project, we are implemented by 7 work packages. In the work package number 1 is focused on creating the ecosystem, the communication platforms, and also the technology design and the construction of the different pilots from the 3 different case of studies. At the work package number 2, we are more focused on developing and demonstrating the biomethane production in technologies suitable more for large scale sites. That is in contrast from the work package number 3, that is more focused in demonstrate the potential of the biomethane that low scale and decentralized biogas plants are widely spread in the rural areas in Europe. So this is the difference in work package number 2 and work package number 3. In work package number 2, we have the case number 1 and the case number 2. And in the work package number 3, we have the case of the case study number 3 that is in Adinkerke in Belgium. For the work package number 4, we are more focused on the valorization of the CO2 that is produced compounds of interest and enriching the cost benefit of the biomethane production in the market that will be validated and demonstrated. In the work package number 5 is the evaluation of the process design and the techno-economic evaluation of the 3 different case of studies. The work package number 6 is all the exploitation and communication work package. And in the last work package is entirely the coordination and the administration of this project. In our activities, well, we start in November of the last year, and we started with a kickoff in Barcelona. Then we have in March our first workshop for the working on the work package 5 in Paris. And in May, we have our first general assembly with the different 16 partners that conform the consortium. And on the next week, on November 15, we are going to have our first webinar that all of you are invited. And also at the end of the month, we are going to have our second general assembly that is going to be in Germany with all the 16 partners that are integrated in the project. Just to see where we are in the Sempre Bio Advance in these 42 months that it's going to take us to build this project. In time, we are in the 29%. In budget, we are in the 2.5. In the milestones, we are in the 38%, and also in our deliverables, we are in the 30% of advance in the deliverables that are already uploaded to the platform on the system on the Horizon Europe. Now, just to have a brief of what we expect from this project. First is to increase the cost effectiveness of the conversion in the biomethane production. This is through the optimization of the biomethane production, the economy of scale in the biogas upgrading in small plants, especially increasing the type and the volume of the different raw materials. Second, we have the diversified conversion technologies for biomethane. Here we have 3 different case of studies with a variety of technologies that we are going to test. And in the third case, we have contribute to the acceptance of the biomethane technologies in the gas market that I think that everybody is trying to put a lot of effort on this to try to get some acceptance of the biomethane in this market. So this will be thanks to the technology, to the techno-economic study from the work package number 5 that we are working for these 3 case of studies. And last is to contribute to demonstrate on the semi-industrial scale of new conversions, technologies to produce biomethane from these different feedstocks, like the wastewater, the wood mass, and the manure. To finish with my presentation, what we have expected, the impact that we expected for this project is, first, the biomethane as a substitute for the imported liquid natural gas. And we know that the biomethane has a calorific power equivalent to natural gas. And just to show you a number, is in the 2020, 81.6 million tons of liquid natural gas were imported. So the idea is to replace like around this 30% of the biomethane in line with the EU 2050 targets. The second one is the biomethane as a fuel substitute in the transportation. We see in the many different projects that we are going to use this biomethane for airplanes, for ships, and for public transport. So if the biomethane specific, the liquid biomethane, reach competitive prices, it will be used as a transport fuel, can be extended. So it's serving as a substitute from the oil-based fuels, reducing the primary energy demand. Also, reduction of the CO2 by 213 million tons per year by the 2050. And this will help to reduce like around the 8.3% compared with the 2020. Also diversify the energy sources of new routes. This is specifically how these projects start to having need to be more brave, because we need to reduce the dependencies from fuels from imported fuels, especially from Russia, and going more through local production of biomethane. This will reduce the need for strategic reserves, because if biomethane and renewable gases are not subject to have a minimum of stock by the European directrices, so the substitution of natural gas with this biomethane can contribute to reduce the minimum natural gas reserves. So this will require less maintaining on these reserves. And just for the end is like less extension of critical infrastructure to protect. And with this, I mean that by promoting local circular projects, we have short distances between where we produce the biomethane and where we consume this. So this will reduce the surveillance of the kilometers of pipelines of infrastructure that we are going to protect. So thank you for your attendance. I invite you, all of you, to follow our projects for more insights and updates. Thank you.
The presentation, which will be given by Odey Codoni from ENGIE Spain. And the presentation will be about the Renewable project, development of hybrid energy storage technologies, and predictive models to transform industries into decentralized points for renewable energy management. So please go ahead. Thank you very much.
Okay, thank you very much. Thank you also to Leitat and Rich for organizing this workshop. My name is Odey Codoni. I work in the engineering department of ENGIE Spain. And as Fatima has just told, I will tell you a little bit about the Regenera project that we are developing with Leitat also here in Terrassa. So just for the beginning, what's the reason of existence of Regenera? Why this project exists, let's say. So the International Renewable Energy Agencies forecast that the renewable energy sources will grow from the current 25% of electricity generation to 86% for 2050. So, of course, this is a good news from the sustainability point of view, but this forecast also entails a lot of challenges regarding the management of energy grids, because as we all know, renewable energies as solar or wind energy are variable and unpredictable. So energy systems worldwide must adapt to this new paradigm in the energy grids. And just for having a little bit of information or a little bit of summary about this concept, I just added the United Nations definition of sustainability, which is meeting the needs of the present without compromising the ability of future generations to meet their own needs. That's being said that, okay, it's very nice to grow the renewable energy integration in the grids to 86%, as it appears there. But we also have to ensure that this energy can be provided to all of us, and so the systems are manageable. So at the end, what Regenera focuses about, and the objectives are very related with that, is that we have to integrate energy storage systems, a large energy storage system for large quantities of electricity and for long periods of time, and energy resources optimization systems just for these renewable energy integrations to be possible. So Regenera project investigates some technologies and optimization models for the distributed electricity storage from renewable energy surplus. Moreover, these technologies are tested in industrial facilities because the scope or the approach of Regenera is to convert the industries not only in energy consumers, like is nowadays the major part, but to also convert them into prosumers, both consumers of the energy and in some way producers or of energy, or being like storing nodes for the energy grids. And also for more added value to this industry, the Regenera technologies, as we will explain later,
are using some waste streams of the projects of the facilities that we are investigating as wastewater or CO2 streams. So for achieving this energy storage, Regenera is focused on two main strategies. One of them is the power to gas approach, in which we convert this renewable energy surplus electricity in green fuels as biomethane, hydrogen, and hythane, which is a mixture between methane and hydrogen. So we can storage this surplus of electricity energy for long periods and in large quantities, which is not possible with state-of-the-art batteries, for instance. And then, of course, the energy management optimization system that has to allow us to couple the energy surplus production with the industry needs energetically and vice versa, because of, as I said, the idea is to we can store this surplus of energies, but then we have to be able to give back this energy to the grid when it's needed. So the energy management system is very also important to for the sake of Regenera. So in a very summarized way is more or less this diagram where we have like the inputs for Regenera, the surplus of renewable energies, and the waste stream from the industry, water or CO2. And then we in Regenera, we've convert that into useful green fuels as methane, hydrogen, or hythane. And then, of course, this with these green fuels, the circular approach, it's very weak. Like we could, with a CHP, for instance, generate power again to the grid, or heat supply, or convert it in green fuels, or even give it back to the industry if they are if they need that green fuel that we are generating. So it's very it can give answer to many energetic problems for the industries, and of course, as I said, the energy optimization predictive models that have to integrate all of these nodes just for being able to function properly. So just for you to know that Regenera is being developed by a consortium of 8 companies and many other external collaborators, Leitat, of course. It's a project with European fundings also into the Next Generations program. And it's for a 4-year period. It started back in 2021, and next year in 2024, it's the last year of the project. So it has 3 main objectives regarding both the energy storage, green fuels production, and CO2 emission reduction, which I present here. First of all, a cost reduction of the storage of renewable energy surplus by 33% compared to state-of-the-art technologies. Also, cost reduction of the green fuels that we are generating as hydrogen and methane by 35%. Also, comparing with state-of-the-art technologies for hydrogen and biomethane production. And then we also made a benchmarking about the CO2 emissions of the industries where we will implement the technologies, which are wastewater treatment plants and brewery industry. And then the objective is to reduce by 25% the CO2 emissions of both on both locations. So as I said, this Regenera project has also a very industrial approach of it's a research and development project, but it has an industrial approach. So this year in 2024, 3 pilots will be implemented in relevant industrial locations. As I said, wastewater treatment plants and a brewing industry, just to escalate the prototypes that we have already developed here in Leitat to a more relevant scale. And that will allow us to validate these technologies for a technology readiness level of 5, 6, to say, which will allow us to assess some techno-economical studies going forward. And of course, I'm repeating myself a little bit, but just for highlighting the importance of the energy management system for for integrate all of the technologies and the external nodes as a power grid or the industrial needs. So the 3 technologies that we are researching in Regenera are, as I show here, the hydrogen production by electrolysis coupled with a water purification system, which will allow us to function with wastewater from the wastewater treatment plant. So we are not concerned about the pureness, or not that concerned about the pureness of the water. It gives us some nice flexibility in terms of the feeding of the process. Then the one that NG personally we are participating, which is a biomethane production with a bioelectrochemical reactor. And we are feeding this reactor with wastewater and CO2. The idea is from the wastewater and the CO2 origin to be the brewing industry. So we are giving some added value or added product in biomethane from 2 waste streams that the industry doesn't want. That's one of the main advantages of this technology. And then the high-ethane production, which is a mixture between biomethane and hydrogen, which is obtained from a coupling of an alkaline scrubber for a biogas stream, which converts the biogas stream from methane and CO2 mainly to only methane, and also a bioelectrochemical reactor from wastewater and the CO2 that we are recovering from the scrubber to generate the hydrogen. So these are the 3 technologies that we are researching. 3 of them have already been developed or constructed and operated into a laboratory prototype scale here in Leitat. And now we are going to the next step, which are the industrial pilots, as I mentioned before. So just also for highlighting the importance of the not only the technological development of the electrolysis, bioelectrochemical reactors, and so on, but also the system that will allow us to integrate all the technologies with the power grid, with the industry, and many other stakeholders for this project. So we are also like a work package of Regenera is the implementation of this energy management system, which will allow us to coupling the industrial processes and waste generation to the renewable energy production to maximize the storage of the energy, which is at the end the main objective of Regenera, and the energy use. Of course, also to be somewhat predictive about the optimal operation of the technologies, because efficiency in storing technologies is very important. We have to try to minimize the losses in the transformation processes from surplus energy to the storage and then to electricity again. And then, of course, to control and monitor that everything it's working okay, and taking into account that the idea is for this to be integrated in an industry. So it has to be more or less easy to control, easy to monitor if everything is working well. It has to be able to be integrated somehow, for instance, in a industry SCADA system. So all of this also is very important, as I said before, to the industries become prosumers instead of only consumers. And for me, a very important node of energy storage and management in the power grid. So just as a summary, and just for you to know that we are working in predictive algorithms with machine learning, which allow us to predict some, for instance, the solar radiation and at the end the renewable energy surplus production. Also, we are implementing some models for the industry side, and then all of that integrated also with the digital operation platform, which at the end will be what we will integrate for the client or the final industry user. Of course, here it's an example, but in the end, with the green fuels, we also could use it in a CHP facility, for instance, or fuel cell, perhaps, for generating electricity back to the grid, or waste or heat to the industry, or many other uses that it could have that also had to be integrated in this model. And as I said, the main milestones, yes, we are finishing, but for summarizing the main milestones of the project, as I said, the laboratory prototype of all of the 3 technologies have been completed. They are here in that. Now we are in the stages of material acquisition and design for the industrial pilots. Will be tested in the wastewater treatment plants and brewing industry. We think that for March, maybe April of 2024, we will have the pilots constructed, and we will start to operate them for the whole 2024 year. And also the big data model for the data collection of the pilots and their predictive algorithm treatment also has been implemented. Now we have to fit this module with operation data. And then, as I said, the next steps will be the erection and commissioning of the pilots, the testing of the technologies that will give us very information of the OPEX, also of the CAPEX and the operation of the technologies, and then the calibration of the predictive model that we are now implementing. So just for finishing, to tell that Regenera is completely aligned with the objectives both in Spain and European policies regarding safe, efficient, and clean energy, because it promotes decarbonization of the economy of Spain with the use of green fuels and more use of renewable surplus energy. Of course, reducing also the energy dependence on fossil fuels, because we are able to produce some fuels with local resources instead of importing them. And at the end, it's another project with a strong support for research and development in renewable and sustainable energies. So thank you very much for your attention.
Next presenter is Luis Rafael Lopez from the University of Girona, presenting to us indoor CO2 as renewable carbon source, coupling indoor CO2 direct air capture to microbial electrosynthesis technologies. The floor is yours.
Thank you for your presentation. My name is Luis Lopez from the Laboratory of Chemical Environmental Engineering, LECIA, of the University of Girona. And this morning I will present you the work titled Indoor CO2 as Renewable Carbon Source and Coupling of Indoor CO2 Direct Capture to Microbial Electrosynthesis Technologies. This work is funded through the Marie Curie Individual Fellowships, and I'm the principal investigator, but I have the collaboration of several postdoctoral researchers, Paolo and Silvia here, and other undergraduate students, as well as senior researchers as Sebastián Puig. The main content of this presentation is, first, I introduce the research motivation behind this work. And then we move to the core of the presentation about the case study of the microbiome process. That's the title of the Marie Curie project. To finalize with the next steps and summary. So the main motivation behind this work is to promote the use of renewable energy and renewable carbon. As you can see, the different sources in this diagram, in order to mitigate climate change. In this presentation, we will focus on CO2 direct capture to produce chemicals and fuels to stop the use of fossil carbon. But why doing CO2 from indoor environments and not from outdoors, which is like how commonly is done? Because in indoor environments, we have higher concentrations of CO2 than this improves what we have the thermodynamical limitation in outdoor environments where the concentration is lower for the CO2 capture technology. So this is for us a potential and explored source of renewable carbon. You might be asking, from where does the CO2 in indoor environments come from? Mostly from us, like human metabolism, we produce about 5%. Also, depending on the type of indoor environment, at home combustion, or in closed non-civilian environments from engine emissions or instrumentation, or we may have intrusion of outdoor air. In our project, we have focused and selected 3 representative indoor environments: school, classrooms, office buildings, and metro cabins, where the recommended value, depending on the country and the health authority, ranges between 1,000 to 1,500 ppmb. However, the CO2 concentration reported in different research studies, they range up to 6,000 ppm, which is higher one is recommended for the health authorities. And this is because we have low air exchange, which leads to what is called bad indoor air quality. We have heard that a lot in this past few years through COVID-19 pandemic, because this is increases the high risk of aerosol transmission. And other effects that I'm not going to enter here, we have a cognitive performance degradation. We don't think well, we get sleepy, we get tired, not because we went to party last night in conferences, we tend to fall asleep, but it's because the air it's heavy. And we feel this a lot of times, and other health issues, but mostly cognitive performance degradation is what we are also interested. And this is an example of CO2 monitoring in a bus ride of 1 hour from Vic to Girona. I carried monitor, and you see how the concentration goes up to 2,000 ppmb, and then when the door opens, it goes down. And the first peak is when the ventilation was not on, and then the ventilation went on, and you see how it goes down. But then I guess they turn it off, and then we have a peak. And then the second figure is just like me locked in a study room with no ventilation, and you see how it increases linearly up to when I open the door. So this is very clear. Concentration is related to us. The traditional mitigation strategies is always ventilation. We have natural, which is like door opening or window opening. We have cross ventilation, or mechanical through mechanical systems, or a mix of both. But there's never a perfect situation. We always have a trade-off situation, whether you apply energy, you spend money, you have good indoor air quality, or you invest less energy, but you have a worse indoor air quality because you have like allergens going in, and this makes the quality of the air worse. So as scientists, we come up with a solution that we have to help the current ventilation systems with a technology in order to not only ventilate, but also recycle the indoor air pollutants and transform them into compounds of interest like biofuels. So this is the microbiome process in the framework of circular economy to transform waste, that indoor air pollutants, into a resource like biofuels. So we propose this modular system that captures the CO2 flow in the air through the first model. I show you later in detail, and then we produce clean air. And later we have a series of models that transform this CO2 into different compounds. This is a schematic of the process. We have first we take the air from indoor environment. We see that from offices or schools, and we flow it through what we call the CO2 microconcentrator model. It's the blue box, where we produce 2 streams. The first one is clean air, and once we have saturated the material, we are capable of producing a concentrated stream of CO2 that then is used in the second step in the microbial electrosynthesis model, where we could transform this CO2 into the compound that we are interested in. This project, originally we focused on ethanol, but then we decided to change to methane. It was more interest in order to be used in situ for example, for heating purposes. Or we can use focused for ethanol production, but then we might need like purification steps that might be complex to be performed in a building, for example. Some details about the first model, the capture unit. This is the goal is to start from indoor air, so a couple of thousands of ppmb to go up to above 90% of purity, if possible, and also to clean the air, to improve the indoor air quality. And this is based on a solid adsorbent material with a solid support, fume silica impregnated with polyethylamine. This is mostly, you know, from exhaust gases, we use liquid amines, but in this case, we have a combination of liquid amine impregnated into a solid support. So we have a solid adsorbent material. We have different support materials that we can test. We have selected this one because show good regeneration capacity. We must do assertions of cycles of adsorption and desorption. So this needs to last a long time. If not, we will spend a lot of money with the material, and at the end, we will be doing something worse. And another thing to mention is like the heat applied during desorption also helps to deactivate viruses. Depending on the temperature and the time, the efficiency of virus deactivation is also effective. So let's go into what we have done in the lab and in the university in Leitat about the first model. This is a simplified roadmap. We started with process design and some evaluation of materials and conception of the prototype, and then prototype automation that took a lot of time and is the core of the work, and then finally to do the experimentation validation. So the Marie Curie Fellowship started in February of last year and ends next January. And in this time, we have developed 3 prototypes. The first one in January of this year, there was like a small box. Basic instrumentation was mostly semi-automated. The second one was like, again, semi-automated because we were working in parallel with automation tasks. And then finally, in October, we have a third prototype that is like fully automated box that is mimicking the whole indoor air capture and desorption. I show you some details here. This is the first prototype. It's a 1 to 100 scale for an ACH. ACH stands for air exchanges per hour. That's the unit used for indoor air quality, to how many times per hour you change the volume of that room. So 4 is a very high number that that later we decrease it to 1 because it's sometimes is not needed, but in this case we selected 4. And experiments focus mostly on the capacity to do the desorption, because the desorption is very straightforward process. It's an adsorption, so you flow gas and CO2 is staying in material, but you want to produce CO2 for the biological model. So we focus on how efficient this prototype was to produce concentrated CO2. We produced a stream of 27%, not much, but it was like a first step that helped us to move forward. And that in the second prototype, we did slightly larger, 1 to 10 for an ACH of 1. And in this case, we managed to achieve up to 45% of CO2. That is what I have not mentioned how we do the desorption. We do flow in nitrogen, heating the material up to a certain temperature, and then we release the CO2. What is still 45% is not what we targeted, and we want to do now is vacuum desorption, because then you use nitrogen. But for the laboratory purposes, it was easier to have a nitrogen flow meter. But now we are working with vacuum desorption. So finally, this is the last prototype we have developed. The third one is what you see before in the lab in different places. Now it's a single box that only has 1 inlet and outlet for the gas and electricity plug. And this, what it's doing is capturing air and concentrating the CO2 and releasing a concentrated stream of CO2. By the moment, it's still not so concentrated as we wanted, but now we have it as for experimentation and validation in the next remaining months. So up to here, this is just some details of the instrumentation. What we're dealing is we're using Arduino-based control because we can do it by our own, the coding. And we have some CO2 sensors to control, of course, the inlet and outlet concentrations and the different temperature probes for the desorption cycle. So this is what is inside the box. And hopefully in the next months we will be able to provide CO2 for the cell in enough CO2. So about the microbial electrosynthesis technology, as mentioned in our group in Leitat, we are experts in this field. So I was bringing the expertise of gas treatment and then coupling the Marie Curie is a multidisciplinary project. So we have to bring something and the group gives you another expertise. So the group was providing me this expertise. There are many cells that are producing methane, but I also started my own to learn and to also understand the needs of CO2 of the cell. We started this flat plate test and with simple materials, nothing fancy, just to have it like as a bench platform. And then the objective of the project is to produce some methane, but have a additional unit to increase the purity of the content of the methane produced in the cell. And that is, we're doing it with capillary reactors. I mentioned, Daniela, the first time they're using membranes. And then we are trying to use it with capillary reactors to enhance mass transfer, because you can have the CO2, but if it's not in the right phase, in the liquid phase, then it's like not having it for bacterial microbial consumption. So this is the cell right now as we have it. It's now operated under continuous conditions. It means like liquid and gas flows in and out. Because also we want to develop a module in the future that we can place it in somewhere and then be producing methane and capturing the air and doing the whole conversion. So we want to learn how to operate this system autonomously. Up to now, we have managed to produce 60% with this cell, but the goal is to go above 90%. So we're doing more experimentation in this direction. Experimentation to learn how to understand the impact of nutrient supply, because the cell might need a lot of nutrient, but if you have it in a building, you cannot replace the nutrients every day. You have to have something in between, like what the cell needs and the practical utilization of the cell in a building, and other aspects like CO2 and hydrogen availability. So this is what we're working right now. As mentioned before, the line in green is methane, so we have ups and downs because we are testing gas and liquid exchange rates. These are some details of the capillary reactor. It's 3D printed columns. Basically, it's a monolith. We have channels of 1 to 2 millimeters, and inside you have the transfer of gas to liquid. Then the bacteria takes the CO2 in the liquid phase. So these prototypes, the geometry helps, the change of geometry helps to increase the mass transfer. And the goal is to install it in the recycling line, so the CO2 that we feed, it's better utilized. So now we're also doing tests. I'm not showing any results right now. And finally, about the coupling, we're also studying are we capable of providing enough CO2 from the prototype capture to the cell? The green line is the CO2 produced, the CO2 needed by the cell, and the colored lines is the CO2 produced by the prototype. So you can see, depending on the nitrogen flow rate, eventually you are capable of providing the CO2 needed by the cell. And so this is okay for us because it means like our scale is right for producing CO2 for the cell. And this is just showing like the first and the second prototype. Because it's larger, the red one produces much more CO2 than the first iteration, which makes sense because it has more material. So just as the next steps, Sebastián is a leader of this next project. It's called Descent. They also want to develop modules, and we already have the first one, and Silvia is working on the second module, on the automated BESS model, to have it in independent modules to capture and utilize decentralized emissions of CO2. So as a summary, we have learned that CO2 is from indoor environments is an unexplored source of renewable carbon, but also help us to improve indoor air quality. That the combination of these both technologies stands as environmentally friendly technological solution to mitigate climate change, and also that this could be suitable to promote sustainable design and energy conservation as principle of green buildings. I just want to extend 1 more minute with this extra slide, because there's always these questions after I give my talk. The people is like, do we really can fight climate change through indoor air capture? Because it's like Indoor CO2 is very diluted. You might think this also like CO2 is not a pollutant. We have other pollutants that are worse than CO2. So for indoor air community, CO2 is not a pollutant, it's a metric. If there's a lot of CO2, there is other things that are worse, but not CO2. And also like with HVAC systems, we have enough to remove CO2. So why all this? And so my answer to this will be, and for you to give to the world too, because you will be asked in the future, is like buildings consume about to 40 to 70% of energy. So they are a major contributor to climate change. And also we spend about 90% of our time indoors. So we're indoor species. So this is my question. What is your indoor age? Just multiply your age for 0.9, and my age is almost 33 years in indoor environments. So indoor air really matters. So we need to improve indoor air quality. And finally, that the capture of CO2 from indoor environments can help to reduce up to 40% of air conditioning requirements. So the impact of this technology can be very significant. So thank you very much for your attention.
Now before this section of questions, Gerald there to speak to us about simulation of virtual use cases for the research project Restore using the web-based process simulation platform Xego. Okay, the floor is yours.
Okay, thank you. Thanks for the opportunity to be here in Leitat again after, I think, 4 years ago. It was another workshop. Thanks for the invitation. And I will present you today, on one hand, a research project that we are involved with, Restore, and also how we use our software tool for integrating the components of in the Restore project and the Restore results into industrial applications. I will first show you a bit about the project, motivation and objectives of the project, the concept very briefly, and then touch the virtual use cases. That's what we then will present in our tool. And in the second half, I will show you a bit about the simulation platform that we are using, the requirements that we figured out, how we have implemented the capabilities, and I will show you a bit how it works. But first to the motivation. Just in the last presentation, we have heard a lot about buildings, energy consumption in the buildings. Maybe here it's the important thing here is the last two numbers that the heating sector in the EU produces about 21% of the energy-related CO2 emissions. And in the Restore project, there is the Restore project makes the effort to use more renewable energy in the heating sector. And we have in the project we've identified several challenges, and also here we highlight the response or the solution that we propose with the Restore project. First of all, energy is, like we saw, renewable energy is not very predictable, and we need storage capabilities to make it available according to the demand. Here, the solution in the Restore concept is to use a thermochemical storage system, which has to be economically competitive. The second thing that we need is to find a way to integrate the renewable energy into the system. For this, we develop in the project flexible heat pump and organic ranking cycle. So it's the reversible system. And the last thing that we have, and this is what we then touch a bit, is the use cases. The system, how can the system apply to different regional situations, different conditions in the EU? And we demonstrate these capabilities with the virtual use cases that we have in the system. So, quick summary of the project: we combine two technologies, thermochemical energy storage and reversible ORC or ORC and heat pumps, and to use renewable energy sources for daily and in particular for seasonal storage. And the goal is to make a high or 100% renewable energies usage in district heating systems. Maybe about the consortium that we have. We have partner project coordinator is CENER, research center here in Spain. We have Technical University in Vienna as the expert for the thermochemical energy storage system. Polytechnico di Milano as a research center for ORC process and heat pump system. Then we have two industrial entities, Durboden, which is a large-scale ORC system producer, and Enabas is here in Spain, small-scale ORC and heat pump system developer. Synthetech, that's where I come from. We are a software company in Austria, and with the focus on process simulation, and we implement a platform for demonstrating the virtual use cases. Aalborg is an expert in Danish company, expert in seasonal storage and district and heating systems. And then we have Steinbeis Institute in Germany for dissemination and exploitation. Andritz is industrial partner who contributes also with application in the paper industry. UBB is a Romanian university. They make the life cycle assessment, and Prospect Institute is a Belgian organization making the social assessment and stakeholder engagement in the project. About the concept, we have in summer, we have typically good amount of renewable energy from sun, CSP, biogas, whatever. And in many cases, a lot of energy is wasted, is lost because we don't cannot consume it. And in the restore concept, the idea is to use a thermochemical energy storage system, which means we have to pump it up. The thermochemical energy system requires a certain temperature level, let's say around 150 degrees C for charging, but also discharging. It has to be heated up while it can be stored cold. So there's no, that's the core benefit. There's no heat loss. So in the long-term storage, it can be stored cold. So we need a heat pump for loading it. And in winter, we again have to heat it up for discharging. And then we need an ORC, organic ranking cycle, to produce on one hand electricity, which goes to the grid, and on the other hand, district heating as use needed by the community. So the ERL of this, the system is fairly low. And here's a short schematic how the concept is validated. Maybe I didn't say in the beginning the project, we are now in project month 26. So we started earlier, 1 year earlier than several projects that we have heard about today. Actually, I think we were in the last call for Horizon 2020. So it's Horizon 2020 project. Yeah, and it shows the various prototypes, but due to the size and the complexity of the system, there will be no complete integrated system available. And instead, we use the virtual use cases to prove how the system can be replicated in various locations. It can be adapted for different facilities in the EU, also to allow us to optimize it for the different situation and to consider the requirements of the final users. And we made the commitment in the project also to make it available, the results in a web-based simulation platform. And here are very briefly the 6 use cases that we are considering. The first one is a residential district heating system with biomass and solar collectors in Denmark. The second one is an industrial plant, actually a cement plant in Germany. The third one is a paper mill in Slovakia. The fourth one is steelworks in Brescia in Italy. The fifth one is a district, is a geothermal plant in Germany again. And the last one is a plant for heating Politecnico di Milano. So it's a small scale district heating system for the university there. Yeah, now, as I said, we made the commitment to have a platform to share the results, but also to make the results accessible and adaptable for others. So we had the requirements which are listed here. We needed a web-based platform so that it can be accessed on a general basis and has to allow the implementation of the virtual use cases. And yeah, make it publicly available for interactive simulation by those interested in the technology. Also, we said it should be possible that stakeholders will be able to create their own testing cases and adapt for their own needs so that potentially the available solutions which are showcased, they grow. Yeah, and the platform was not just for the project use, but should also survive after the project ends. So for us, for implementing the platform, we didn't start from zero. We had internally a system which was is a desktop system, which just with some brief characteristics, it's an equation-oriented process simulation framework. It defines a very generic structure so that it can be quite well adapted for different applications. And actually, we have in-house for various cases. We have standard application available. which are represented by what we call model libraries. But there's also a tool available for directly for creating new components, for creating new model libraries to adapt it for specific requirements. And also something that in the last line, it's separates the user interface from the simulation core, from the kernel, which is quite important, was quite important for us to get it in the make a web-based system out. And maybe the other thing, which a bit links us back to Leitat, here we have been working together in a project called Midas, and there we have already made some prototype in this direction. So get our feet wet and learn a bit how we could proceed with the system. And what we have now in the project available, about roughly after half of the project finished, is a platform, we call it ipse-go, with these characteristics. First of all, it's a cloud-based, cloud native, I have to say, in this case, simulation framework. So the only thing that you need as a user is a browser and an account for at least for using the more detailed features. But also the system came, I mean, we have this in mind for the dissemination of the project. It allows to integrate parts of it, project results, into websites for presenting in detail the results. And also for the internal use, it's not to neglect something. It's also supports a collaborative development work on the project. So you can very easily share, exchange information, and carry on. It's not, there are also some aspects that maybe I should not totally neglect here. I have to mention it because cloud system or web-based systems very often as considered as something very trivial to use. You can use it just with a few clicks. It has its challenges. It's because the task is challenging. So some expertise is required, but it's easy to master. And it's also consequently with the target audience that we have, it's important to take into account the needs of these different usage levels. So from the project, we saw we will have to cater for occasional users who just want to have a quick overview. We may have users who want to play a bit with the data, but also the users who might go very deep into the details of the system. Yeah, I will show you a few views of the system. Most of the things are available on the web as well. So we have a project page which is with a description. We have components available. So this is, I think there's a link up there. You can see with this link you can access this. It's generally available on the web, and it somehow look into the system without any need to register to anything. So we have I've mentioned the use cases. They are emerging. They started now in 2 months ago, so we started implementing the use cases, not only the framework. So there are still some placeholders. So these are, you can view. You can also see it more in detail. And this is automatically generated from the project results that we have. I have mentioned it's possible to embed it in website. So that's how we plan to elaborate more on the use cases with some text, maybe, and then also with some way to interact with changing some data. And no, okay. And for the expert user, really have, I mean, you need an account, and then you have a fairly detailed way to work on the system. You have a catalog of projects. You can create new projects here. So this is a view at the dashboard. Projects, let me see. Yeah, this is the one part of the restore system. You see here, this is the project editor. You have your components. You can place them in the flow sheet. You can arrange as required, provide data, run calculations. So this is the core system, and you can decide that the project is now in a level where you want to share it with the public, and then it's available as I have shown you before. We have project templates. These are the example projects. We can use the existing use cases and modify them. Yeah, I have used it now in this with screenshots, but we could, in principle, also we could just go open a browser and bring it up and go into the details if somebody is later interested. So the current status of the project is the basic framework is ready to use. The platform is available. And actually, with our standard library, it's already quite intensively used. We have nearly 10,000 calculations per month going on in the meantime. But it's further developed. It's going on. We have some capabilities in the next few weeks. We will have the capability of scripting it and using and generating charts like temperature entropy diagrams or whatever is characteristic for a specific application. And we're also going to integrate time series calculation, dynamic calculations. We calculate an annual profile, for example, and an economic analysis, which is done by Senea as project partner. Yeah, and I've a bit tried to emphasize the separation between framework and project. So for the project itself, the model library is being developed. We are reaching nearly completeness. Basic components available. Some refinements are still happening, and then, of course, we create the project, the virtual use cases as projects. Yeah, brings me to the end of the presentation. Thanks for the attention, and I have, in case it interests you, I have here a few links. On one hand to the project homepage, on the other hand also to the web cloud-based application. Thank you very much.
But you can also stand up there. So is anybody listening? Okay. So I would invite the audience to now make their questions to them if there is any, and at least one for, not more than one for a presentation if possible because of our time constraint. Any questions? I'm not sure if it's still working. I didn't finish the turn from the last time, but we can also speak loud.
Okay, so as a question, but I think it's okay.
Yeah.
Interesting, because obviously the use case for the chemical storage for longer term storage of energy. I was wondering how it compares against other long term storage options like pumped hydro, for instance, and what the advantages are of it over something like that.
Yeah, actually,
And the advantage for using the power to gas for the long-term storage of surplus energy. First one is that there is already an infrastructure of gas networks and it's said that the hydrogen also will arrive. So it's optimal way of storing the surplus of energy with actual infrastructure. And then also green fuels give some flexibility in terms of we could convert it again in electricity with a CHP or whatever, but also it has the potential to convert it in fuels for mobility or maybe some chemicals. Or it's like the options are much larger than with batteries or pumping hydro or other sort of things.
Great, thank you.
Any other question? Okay, please, Andre and Nicholas have questions.
I have a question to the rules concerned with renewable energy. I like it very much idea because it can reduce the energy consumption for ventilation. However, I have calculated how much of this CO2 can be removed. And I took the example of the school of Leitat, and it is more or less 80 kilograms per day. How do you imagine, how do you plan to transport this very small amount of distributed CO2 to the central plant when it will be used?
I'm not sure if it's.
Well, no, it's not working. So,
No, I did not explain it, but the idea is to use the CO2 in the same place, because if you add transportation or storage, this increases the amount of energy and money and cost for the installation. And about the amount of CO2 that is captured, we see, at least I see that the hydro CO2 is a piece of the cake of the whole CO2 cake that we need to capture or remove from to get the targets for the European Union. So this is, if there's not a lot of the CO2, but it's a part of the CO2 that not only is what you capture, but what you avoid of the energy used for ventilation. So this is like two parts: the CO2 you get from the air, but the CO2 that you avoid from reducing ventilation needs. So this is both, and the idea is to have also, this is like a change of mentality. In the future, we have to make new buildings like we have now at home, like laundry for clothes. Now we will need to have laundry for air, for example. So we will have at home a system for removing air. So for home or apartment, we have that single unit. So it will be like in the same place. So you avoid transportation and so on.
Nicholas?
Yes, I have a question to Antonio and the Stakeholder project. You mentioned the biomethane production by pyrolysis from the woody material. What happens to those? What is the solid product of the pyrolysis? What do you do to it?
Yes, well, our partner is Terawatt from France is working a lot, and they've been working like for a lot of time with, of course, especially with biochar, and they are planning like many kind of different uses, but specifically for soil.
Anyone else from the audience? Otherwise, I have two questions. One is for Antonio. So Antonio, you are, yes, Antonio, you are representing a cluster with hundreds of companies, and we would like to know, how do you think that the concept of the projects that you have heard here today, especially the hosting workshop project with Netfuse, could be a message to pass forward to your cluster companies?
I think that the future for cluster is to build a consortium between different stakeholders that are working together, like public interested and the prices like us that we are engineering, but you can work together with the people who is building the machine. At the end, if in all the process, in the civil process, is involved all the people since the beginning to the final user, you can do it a better option because all the questions is integrated since the beginning until the end because the stakeholder or final user is working with you and the producer of the equipment is involved too. So I think that the cluster is like a consortium for all the stakeholders in the project, since the beginning until the final user.
So the next question will be to CTEC, and I think we want perhaps to reinforce how important it was for the acceptance of the Restore project to have the virtual platform to validate 6 different use cases.
Yeah, definitely. I think this was a one key point in the system because it was not possible to validate the system due to costs to restriction that you definitely have at such a level to get some convincing applications and study some convincing applications. And I think the concept of having it really available and having it let's say dynamically available for stakeholders, I think this was quite an interesting aspect in the assessment of the project. And also we see it. I mean, the working on the project, it's a high level of complexity with many degrees of freedom where how you integrate the mass flows, how you integrate heat. You see a lot of potential for improvement or making things wrong, and then you can play with a tool like this. You can experiment, and of course, if then the outside world comes to interact with the concept, then it adds some extra degrees of freedom.
Thank you very much. So if we don't have any other comments or questions, I would thank all of you for your excellent partners here present. I also thank the audience for coming and giving the prestige to our workshop. We were really touched to have you here and to have your participation. Thank you as well. I want to Leitat, our host, to think about the next step of the day, final step. And but before we have the conclusion, our coordinator, some words on Andrea Conti.
The of the next year project, I'm very pleased of what we have done during these 2 days, and also this session on with the stakeholders has been quite a success. I think we are going in the right direction. The partners work together very well. Results are coming, so we are ready for another year of dense work, and I hope next year we will have more results to be presented to stakeholders both in Spain and in the other countries where the partners are have their seats. So I thank you, the organizer, especially Eduard and Daniele, and I give the floor to them to say a few words if they want. So thank you very much.
more complicated because most has been said already. Just thank the project coordinator for allowing us to organize the event. Also Fatima and Chris for helping us in setting everything, the agenda. Also for the speakers to come here. But just the final words, I really hope that today's event has served to all of you to know about what we've been doing so far in the Net Fuels project, what we are working on it at this moment, and also if you could have some nice ideas for future collaborations or to raise awareness of what we are doing. And I think that now it's the time to go outside, enjoy some lunch and continue the discussions that because there are a lot of possible collaborations and interesting ideas to share. So I invite you to go in the hall and enjoy some more time with fruitful discussions. And thank you very much again.